I'm going to be speaking about decarbonising energy systems, particularly from a materials chemistry perspective, and how you sort of upscale materials from academic labs to industrial systems and get them deployed, and some of the considerations that go along with that. So I'll split the talk into two parts. Firstly, in terms of domestic applications, so combined heat and power units that use solid oxide fuel cell technology. And in this section, we'll explore the importance of materials chemistry, and in particular, what it takes to have a successful collaboration and achieve these goals. And then we'll look at industrial applications, focusing on the spirit distillation sector in Scotland. In particular, looking at energy intensity of the process, how we can use biomass electrolysis as a potential way to generate fuels for the distillation sector, and some notes on heat recovery and using local renewable energy. So just a slide of text to start. According to the NAO, in the UK, around 18% of greenhouse gas emissions come from domestic heating. And there are many ways that we can kind of look towards decarbonisation. Obvious way is electrification, usually via heat pumps. These are the most efficient way to do it. But there are some challenges with deployment for heat pumps, like cost, the ability to retrofit these kind of systems in houses that aren't well insulated. They're much more sensitive to poor installation, for example. And we also have to look at, if we shift load essentially from a gas grid onto an electrical grid, can our current grid infrastructure take it if we put every house onto a heat pump? Other ways we can look at blending a percentage of hydrogen into the current gas grid. We can do that up to about 20% volume at the moment for hydrogen. Most new gas boilers are able to accept 20% hydrogen. And the one that we'll be looking at today is combined heat and power, or CHP systems, which offer flexibility because you can easily retrofit them into houses, but they're extremely expensive, so it's a really tough market to crack. You may or may not know, we actually had 5 of these CHP systems manufactured by a Swiss company called Hexis around campus. There were about 3 on the scores, 1 in the Buchanan building and 1 on North Street, until about a month ago when they were all ripped out. Unfortunately, Hexis no longer exists, so they're no longer certified, but they ran for about 7 years to reduce our CO2 emissions from these buildings whilst delivering power to them. And this is what it looks like. So this is in the Buchanan building. Most of the stuff in that room you probably recognise if you have a hot water cylinder and a boiler at home, but the unit on the right, let's see if I can get a pointer, over here, that looks sort of like a fridge freezer, is a combined heat power unit. So that was able to take care of all of the heating and hot water demand for a small family home, as well as give a 1 kilowatt electrical power output, so you're less dependent on grid electricity as well. So what are fuel and electrolysis cells? So they're electrochemical energy conversion devices. So if we look at the example on the left here, a solid oxide fuel cell, I'll explain what that is in a moment. Rather than mixing air and fuel directly and burning it in a boiler, here we're actually separating the 2 compartments with a dense solid oxide electrolyte here, and it has 2 electrodes, one either side. We feed air into the air electrode on the right-hand side there, and the oxygen dissociates, and it's able to migrate through that dense electrolyte material to the other side, the fuel electrode. The fuel electrode, we can put pretty much any kind of fuel in if we're using a high temperature fuel cell. And here the hydrogen, for example, that you put in splits up, releases electrons to this external circuit, which gives you your current with power, and combines with the oxygen to give a waste product like water, for example. So as I said, this process generates electricity. We call these solid oxide fuel cells because the electrolyte material is made from a solid oxide zirconia material. And in order to allow this sort of migration of oxygen through the membrane, we have to heat it up to at least 600 degrees, usually higher. In our case, we were using about 850 degrees. So that means you have a lot of high-grade heat that you can use, which makes solid oxide fuel cells great for combined heat and power applications. SOEC, as you might expect, or electrolysis, is the exact opposite. We're using renewable source of electricity to convert steam, for example, back into hydrogen. And the good thing about high temperature systems like this is that you can also use gases like carbon dioxide, convert them to carbon monoxide, which would otherwise poison the materials in sort of lower temperature devices or alternative electrolysers that are available. So you can see that these are inherently interrelated processes. So how do these relate to a system? Well, in this Hexis Galileo system that we had installed at university, in the top portion we had a stack of these cells put together and separated by these interconnect plates, which help to connect them electrically and also distribute the gases into each compartment. You can see here there's a cross section of the fuel cell, so the air electrode faces down, the electrolyte's in the middle, and the anode is facing upwards. And this particular stack had 60 cells in it and gave a 1 kilowatt power output. It also had about a 2 kilowatt thermal output, which was contributed towards your sort of domestic heating and hot water, and there was a backup burner in there as well to provide the rest of the heat load. So in these systems, so the air electrode and the electrolyte are pretty standard for the standard materials for this kind of fuel cell. They don't pose too many problems, and we know them very well, how they behave, but that's not necessarily the case for fuel electrode or anode here. The state-of-the-art material used for this is a composite, and it's a mixture of metallic nickel and either yttria-stabilized zirconia or cerium gadolinium oxide, YSZ or CGO. And the idea of this composite material is that the nickel component provides good electronic conductivity, and the ceramic component provides good oxygen ion conductivity. So you've got to have a good mixture of these to have a high performance from your electrode. This is the state of the art and probably has been for at least 60 years, mainly because it has good electrocatalytic activity for hydrogen oxidation, good ionic and electronic conductivity, as well as good mechanical stability. It's really robust. Unless you're developing a system that has a lot of fail-safes in it to kind of protect this electrode material if anything unexpected happens, it does have quite a few shortcomings. So the nickel phase is particularly sensitive to emergency shutdowns and any kind of harsh treatment, really, particularly if you want to get rid of your fuel processing unit. So you're not reforming it in from, for example, natural gas into hydrogen and carbon monoxide. Nickel doesn't particularly like methane, for example, because it degrades and deposits carbon onto the nickel, which then deactivates it. Also, if you don't strip out the sulfur that we use to odorize our natural gas in Western Europe or around the world, that will poison it too. But the main reason that it's particularly bad is because of its intolerance to redox cycling. So, like I said, if you don't, in your system, have a way to keep the nickel exposed to hydrogen or fuel gas all the time, it will reoxidize. And when nickel reoxidizes to nickel oxide, it has with it a 41% volume expansion, which basically rips your cell apart. So, not ideal. I guess the question is, how do we address this? And probably the easiest answer is get rid of the nickel, right? Easier said than done. In order for that to take place, you would need a single phase backbone material that is capable of having good ionic and electronic conductivity within that single phase. It's got to be redox stable. But if you can get a good microstructure, sort of as the model suggests here, you can then activate it by putting pretty much whichever catalyst on top of it that you want. Probably over the last 30 years or so, a class of materials called the strontium titanates have been in focus. And at the start of my PhD, I was sort of presented with this material here, the lanthanum strontium calcium titanate material, and asked to try and develop a good microstructure and a good fuel electrode for Hexis system. So I spent a good couple of years at the start of my PhD optimizing this to get high porosity so the gases could go in and out, good connectivity of the backbone here so that you have this electronic and ionic conductivity throughout, and also strong adhesion to the electrolyte down here to make sure that it didn't break away from the rest of the cell. As I said, it took about a couple of years, but the trials and tribulations were worth it because pretty much as soon as we put even a pretty rubbish catalyst in, it had a really high performance. And we spent a further year optimizing that to determine which was the best catalyst to use. It allows you to tailor the performance to whichever application or whichever fuel you're using. It means that you don't get any structural rearrangement because everything is on the surface of the electrode. And it means that you can use the minimum amount of catalyst, so you'll bring it down costs and making it slightly more sustainable for the rare earths and platinum group metals that we often use in these systems. So skipping ahead probably 3 years after we got some good performance, we were invited out to Switzerland to test some of these cells over thousands of hours. And this was one of the cells that went really well. The important point in this information on the right-hand side here is that we have our perovskite material as the anode backbone, and we impregnated some cerium gadolinium oxide as a catalyst, as well as a low loading of rhodium. And that's what gives this really stable data trace in terms of voltage over time. Now, when we look at how much it degraded, 3.2 milliohms per 1,000 hours, that's actually still about an order of magnitude higher than you need for a commercial system. So even though this is good, really good performance for this class of material, it's still quite a way away from what we needed to get it into the Hexas stack. But this is where the materials chemistry side comes in and the importance of it. I think a lot of people think that, you know, your battery in your phone is just a black box filled with nuts and bolts and nobody really knows or cares what goes on in it. But you really have to engineer these things down to the nanoscale to make them work and make sure they're to specification. So what we can see here in this analysis, it's called AC impedance spectroscopy, and it's quite routine in our labs to test fuel cells. This plot of resistance versus frequency shows all the different processes happening in the fuel cell. You can see there's 3 here. So the low frequency one relates to how the gas is diffused in and out. The middle frequency one relates to the air electrode processes, and the high frequency one relates to our fuel electrode. And you can see it's this one that's increasing in resistance and decreasing in frequency over time. So quite easy in this case to work out what the culprit was. We can then correlate that to what we see in the microstructure and even the nanostructure of the electrode. So this is a broken section of the electrode, the fuel electrode. You can see we have our perovskite material here, and it's coated with a layer of the CGL on top, and it harbors this field of really tiny rhodium nanoparticles here. You can see that some of those nanoparticles have agglomerated, but only to about 50 nanometers. And that's essentially what's happening here. Is the reason we were able to get such longevity in terms of the performance was because they stayed so small for such a long time. This analysis over here shows sort of the X-ray response of some of these areas of the electrode. And what we can actually see is the rhodium particles here, highlighted in red in this graph. They're actually socketed into the CGO material, and that's what pins them to the backbone and stops them from moving about and declining in performance over time. So the Hexas were really happy with this, but we decided that the next step was to upscale it and try and get it into something that resembled a small system. So it took multiple campaigns. There was certainly no success without a lot of failure. And the collaboration process was key to actually getting it into a system in the end. Our first attempt at upscaling it to a stack, so we went from a cell that was about that size to one that was about that size, if I aim at the camera. And then we stacked 5 of those together. And you can see here that the performance was pretty poor. Suddenly that sort of reasonably low degradation that we had in our small scale cell had disappeared, and we ended up with 20% degradation over less than 2,000 hours. When we looked at the microstructure, it was pretty awful too. You can see that in this case, those rhodium particles, as shown here, had sort of stuck together and we'd lost surface area for the catalyst. Now, until this point, there was sort of a personnel change at Hexas, and back in 2015, when I was originally invited out to Hexas in their labs, they were extremely cautious about what they told me. Certainly didn't trust me with the company secrets. And I remember going down to the test stand downstairs in their labs once, and they were about to apply a certain layer before they put the cell into the test setup. And he picked up a stool, walked 5 paces away from the bench, and sat me down on the stool and said, you can't come any further than that. That was the level of distrust they had at that point. It was pretty obvious what he was doing anyway, but I played along. So when we had this personnel change, I'm making him out to be a horrible person. He wasn't. He was absolutely lovely, just extremely cautious about trade secrets. But we had a personnel change in 2017, and he really pushed this test through. And when my new supervisor saw how badly this went, he said, right, enough's enough, let's actually tell you how we make our electrodes. And maybe we can get this into our system, because it actually solved a lot of problems for them. And we reported these results, which I'm very proud of, and they're all very nice. So if you want to look at the technical detail, you can have a look at this reference. But my favorite section is actually a section on collaborative approach, which was written by my colleague, Mark Cassidy. So just highlighted a few areas of this. I won't read through it all, but the key requirements were to generate shared goals and understandings through fostering close working relationships. Regular informal communication, as well as more formal things. You can't just have 6 monthly update meetings where nobody visits anyone else's lab. It doesn't work. We had multiple exchanges between Scottish and Swiss labs up to weeks at a time, so that we could really get into each other's labs, understand what processes were happening and what the differences might be, and why we weren't seeing the same things in academic labs that we were in industrial labs. And the only way that really this can come about is if they trust you. So having this constant contact, telephone conferences or Teams meetings every month for 8 years, I guess it rubs off, but you have to build that trust, otherwise you'll never end up with a good collaboration. It's amazing the number of collaborations in which information is withheld and it holds up the process. Within about 6 months of them telling us how they made their electrodes, we got this performance, which is not only a lot more stable, but it actually beats the performance of their industrial standard cell. It's stable to a lot of different harsh treatments. So redox cycling, that's where we switch between hydrogen and air environments. It's fully stable to that. Thermoredox cycling, that's where we also drop the temperature at the same time. It can withstand that. Our cells can withstand exposure to sulfur. So if the unit breaks down, which strips the sulfur out of natural gas, ours can recover from that exposure very quickly, whereas the blue curve there, that's their standard cell, is actually starting to degrade a bit. And then we do a particularly nasty treatment called overload, which is where we keep telling the stack to provide current, but then we turn its fuel supply off. So it's screaming by this point, but again, our cells can recover from that very quickly. And if you continue to do overload cycling on it, actually, after 2 or 3 cycles, their state-of-the-art cell just dies and can't recover. So if you'd like to look into any more of that data, you can have a look in this reference down here. Again, 4th generation, that was probably another year on, and we got it to the degradation rate of 3.7 millivolts per kilowatt hour, which is industrial standard for Hexas. And then we did eventually get it into a full system. So we stacked it up, 60 cells, and put it in to this system here, which was actually manufactured by Wiesmann, who are a German heating and refrigeration company. You can see that actually we very successfully reached the 1.5 kilowatt peak power output, but there were some issues with the stack construction, which meant that there's a lot of instability here. It wasn't just our system that was affected, it was a lot of other systems that also had Hexas standard cells in. And essentially at this point, the company was shutting down. The owners had starved them of any cash, and there was a lot of staff turnover, so maybe the systems weren't as prepared quite as carefully. So it's a great shame that we didn't get past about 300 hours of testing. We were anticipating tens of thousands of hours, and they were very interested in taking it commercial. But none of this could have happened if the collaborative process wasn't as successful as it was. Okay, so that sort of wraps up the domestic side of things. We'll try and quickly go through the other project that Paul mentioned at the start, which was a knowledge transfer partnership between University of Strathclyde and R&B Distillers Limited. So Isle of Rassay is located between Isle of Skye and the mainland over here. And they have a distillery there. Very beautiful place, and certainly the best views of Skye that you'll ever see. And R&B Distillers Limited were interested in decarbonising their distillery in the most holistic way possible. So I joined the project to try and advise them on that. Now, in general, in the distilled spirits sector, 80% of the greenhouse gas emissions are thought to come from scope 3 activities, which is basically everything brushed into one sort of bin that is not attributed to scope 1 and 2, which is essentially burning fuels either on or off site. But that 20% that remains in terms of scope 1 and 2, it might not seem much, but actually when we eventually get down and reduce sort of the emissions associated with transport and making bottles and growing barley and all that kind of thing, it's going to be quite significant. Most distilleries report an energy content of their alcohol for to 6 to 10 kilowatt hours per litre of pure alcohol. But some older distilleries which have more traditional setups, should I say, will be well over that. So the question is, how do you decarbonise such an energy-intensive sector? If you look at the sort of a brief overview of the production process, we have the mashing process, which makes wort, which gets fermented with yeast to produce wash, and that is then passed on to a double distillation step. From the mashing, we get a waste product of draff or spent barley, and that's usually fed to cattle or sheep on Rassie. From the wash distillation, we get pot ale, which has a lot of dead yeast in the bottom of it, and from the spirit distillation, we get spent lees, which doesn't really have much of interest in it for our purposes. But both of those are discharged to sea in line with SEPA guidelines. For the Isle of Rassie distillery, we did a bit of an energy and CO2 audit. So you can see that most of their emissions and sort of energy content comes from the kerosene that they used to burn in their steam boiler. They used to be on red diesel until March 2022, until the government hiked the duty on it. And shockingly, they switched to kerosene, which has no duty and no climate change levy on it, for whatever reason that may be. But in total, if you add up all of their different fuels, they come out at the top end of that range that I spoke about before. And if you also include the CO2 from fermentation process, which is somewhat taken into account when the barley is grown, we're at over 3 kilograms of CO2 emitted per litre of pure alcohol made. We also have quite a lot of waste. So this is per mash. So if you want to work out their daily waste, you just multiply all of that by 2. They do 2 mashes per day. So we were looking to see if there was a way of converting some of this waste into hydrogen that they could then displace kerosene within their boiler. So as I said, we were using over 160,000 litres of kerosene a year, and we were trying to displace some of that with hydrogen produced from a biomass electrolysis process. And the reason we were looking at that was because biomass oxidation, sort of in an electrochemical cell, occurs at a lower potential than standard water electrolysis. So the efficiency would, and the energy input required for it would therefore be higher. And to do this, we were looking at polyoxometallate catalysts, which are hideously corrosive and not particularly nice to work with, to be honest, but they were really good at oxidizing biomass. So when you mix this bile yellow phosphomolyptic acid, which was dissolved in water, with some biomass, it would strip off protons and electrons when you boiled it at 100 degrees for 4 hours, and it would turn this sludgy blue color. That reduced polyoxometallate catalyst could then be fed into the anode of an electrolyser in order to generate hydrogen for that process. Now, it's important to note here, this isn't a solid oxide electrolyser. This is a lower temperature one called a proton exchange membrane electrolyser, and the material sets are very different. So it's what we call a Nafion electrolyte, which is a PFAS chemical, and the electrodes are typically made out of carbon and platinum. We noticed some strange things happening during our experiments, and we ended up going to a particle accelerator called Diamond down in Oxford to probe what was happening. So you can see here at the start of the experiment, we're firing an X-ray beam through our setup here to understand how the catalyst is changing as we actually do the electrolysis experiment. And we're still trying to work out what exactly is going on, but there should be a publication out soon on that. But what we essentially found was that if we took all 1.5 million litres of pot ale that was discharged a year and all 420,000 kilograms of draff that was produced every year, in theory, based on how much hydrogen that catalyst in a particular concentration could generate, we should get about 5.4% of the hydrogen demand fulfilled. In reality, because of inefficiencies with the process, we were achieving about 2%. We did make some improvements towards the end that got us up to around 3.5–4%. But even at 5%, that's clearly not an economically viable thing for a distillery to do, given that this is a technology readiness level 1 or 2, something like that. So at that point, we decided to change tack and look at what could we actually get that's on the market to decarbonise the distillery. And probably quite obviously heat recovery is key for this. So, and you get economies of scale and efficiencies of scale as well. So in distilleries that operate 24/7 and have a really high throughput, you can use techniques called vapor recompression. So if you're making at least 500,000 litres of alcohol a year, you can use thermal vapor recompression. And if you're making more than 1 million, mechanical vapor recompression. Essentially what it does is it recycles heat from the stills via thin film condensers, vacuum pots, and recompression steps. In the case of thermal vapor, that's a nozzle of steam or a jet of steam that comes from the boiler. In the case of mechanical, it's done by electrical compression. But as Shivers Brothers, their Glentorquers distillery, have demonstrated, they can get the sort of energy content of their alcohol down significantly. I've heard that 2 kilowatt hours per litre of pure alcohol is possible, which is incredible, frankly. Other things you can do: don't reject the heat and hot water. You think about it, we're just heating up, we're burning kerosene to heat up, make steam in a boiler, which is then going towards the stills to evaporate your alcohol. Once you've heated it up, you don't have to cool it down to condense it. So you don't have to have a cooling tower out the back to reject all of that heat, which doesn't make any sense to me. The obvious thing to do, and it's going to save you money in terms of operating costs in the long term, is to have heat recovery through heat exchangers or these sort of TVR processes. And it doesn't have to be expensive either. Knockdhu Distillery is a really good example. They did it on a budget, effectively. They cut the back off 2 water tankers, buried them underground and piped it all into their condensers. And they say that they use the water 7 times before it gets discharged out into the drain, because they're constrained, particularly in the summer, by their water supply. Another good example from just down the road in Glenrothes is Inchderny Distillery. Here they send their draff and pot ale to an anaerobic digestion plant just over the road, and in return they get biomethane back. They've coupled that with TVR, and they can get down to about 4 kilowatt hours per litre of alcohol. And we also have the first movers on heat pumps and hydrogen now. Ahaska Distillery in Galway are using high temperature heat pump really successfully. A lot of people didn't think that it would be possible, but it is, as it turns out. And Logan Energy and our Beaky Distillery partnered up as part of the Green Distilleries Fund, and they were awarded £3 million to put in, I think it's an alkaline water electrolyser. They've got a 1 megawatt wind turbine, they've got storage and a hydrogen boiler. So they've displaced about 50% of their diesel just by doing that. To my knowledge, they don't have any heat recovery though, so it seems a pretty obvious thing to do as a next step, is put that in, and I'll get that down even more. The final thing I'll say is that everything is sort of specific to location. You know, not every distillery is going to be able to operate 24/7 and take advantage of these efficiencies, but you should use what's in your back garden. As Paul said at the start, I'm now on the board of directors of the RAS Community Renewables project. So in November 2022, they had a turbine house commissioned. We've got 2 turbines with a peak output of 137 kilowatts. And unfortunately, because the grid in Broadford is so weak, we can't export more than 50 kilowatts at any time. So at the moment, we're trying to negotiate with the distillery to supply their warehouse site and accommodation site, so that we can sell them green electricity. And obviously that's good for them as well, and they should get it cheaper than the rates they're currently getting. So just to sum up, hopefully I've shown you that materials chemistry is really important in delivering these next generation energy systems. They aren't just black boxes, and a lot of effort goes into making sure that they function as they should, and they're of the highest efficiency. Collaboration is key. You have to make time for everyone's perspective, understand what's going on in everybody's labs, build trust, and be honest about everything, otherwise it's likely not to succeed. Regardless of whether it's domestic or industrial, heat recovery is going to be the key to most things, as with heat pumps in domestic situations. There's a plethora of technology about, but there's no silver bullet, so it's about putting the right technology in the right place. Something that's the most efficient and cost-effective solution, or what I would call common sense engineering. Final note is that we actually have now a fuel cell production facility alongside the Colin Vincent battery facility down in Eden campus. So we're able to produce anything from our ceramic powders at the start of the supply chain, characterize all of them, incorporate them into inks and slurries, which can then be made into fuel cells using the state-of-the-art screen printer and belt ovens and furnaces down here. So if you're interested in this, please get in touch, or you know anyone who would like to use this facility for any kind of ceramic processing research, then yeah, please do get in touch. Some acknowledgements. So from the distillery project, Ed Brightman, Jun Lee, Lewis McDonald and Stephen Leave, as well as Luke Keenan from Diamond and the University of Strathclyde in here. We took this picture at the start of the experiment as we were too afraid of looking dishevelled after 48 hours without sunlight here. So we still don't look great either. But and also Alistair Day and Norman Gillis from R&B Distillers Limited, Innovate UK and the KTB West of Scotland for their support. And for the projects at St Andrews, of course, John Irvine and Mark Cassidy, Christian Savagna, David Miller, Aaron Naden and the whole group, and Andreas Schuler, Jan Grolig, Andreas May and Holger Bausinger from Hexus, and of course EPSRC for funding. So yeah, thanks for your attention and welcome any questions.